Welcome back, ladies and gentlemen. Today we are going to continue our discussion in Unit 3, focusing primarily on what is known as quantum theory. So what we've discussed previously is where electrons are actually located around the nucleus. You probably look at the picture that's present in the front of this video and would think that those electrons orbit in set paths around the nucleus. And what you're going to find is that when we go in and discuss more about quantum theory, that is not the case. So let's go ahead and jump right in. Our learning targets for today, you will be able to explain the wave-like properties of electrons and how that relates to how they exist outside of an atom. You'll also be able to understand some basic principles of quantum theory and evaluate the concept of quantum numbers and how they help determine the probable location of an electron. A lot of heavy stuff this particular video. Hopefully you'll be able to follow along and we'll be just fine. So, just a couple of key vocabulary terms. You've probably never heard of any of these before, but we're going to be discussing things like the Heisenberg uncertainty principle, a little bit about quantum theory, orbital, and then a variety of quantum numbers that help us determine the specific or rough location of an electron in the outside of the nucleus of an atom. So we talked a little bit about last time. We talked a little bit last time about how light exists as a particle. We used the photoelectric effect demonstration to get a better understanding of that. Well, a man by the name of Louis de Broglie did an experiment on light in order to determine its wave-like behavior. And he did what was called the double slit experiment. So he took a light, or in this instance an electron gun, and basically shot that through two slits inside of a piece of paper. Okay, it's known as the double slit experiment for that particular reason. Now, normally you would expect on the wall that is beyond that, the one on the far right-hand side, that all you would see is light from two small slits that go through it. However, what he found was an interference pattern that was located on that back right wall. That interference pattern indicates that some of the waves from both slits interacted with one another and either amplified or canceled those waves, which is why you see the interference pattern on the right-hand side. That indicates that light must behave as a wave, that is, that it has a property about it that gives it amplitude and gives it frequency. So when we talk about quantum theory, it describes the fact that electrons and light itself has both a wave and particle presence, a wave-particle duality, if you will. The Heisenberg uncertainty principle is based on the fact that light exists as both a wave and a particle. And this is something that's very important. It is impossible to know both the position and velocity of an electron at any given time. I kind of equate this to kind of a race car on a racetrack. So I took a picture, or there's a picture of a race car that is here. Now we know its location on the track because it's stationary in the picture. But based on the picture, I have absolutely no idea how fast that car is going. On the opposite side, if I know how fast the car is going, it would be very difficult for me to pinpoint the very exact location. Keeping in mind that electrons, unlike race cars, move at the speed of light. That means that it essentially would be able to rotate around the Earth about 10 times every second. So light moves very, very quickly. It would be very difficult to pinpoint the exact location if we know the velocity and vice versa. So based on this information, we really can't describe electrons moving in orbitals because we would know their exact location. So we assume that they exist in regions located around the nucleus known as orbitals. These are three-dimensional spaces where the electron is most likely to be found. So how do we describe orbitals? Well, each electron is given 4 quantum numbers that describe the properties of the electrons in those orbitals. So, for example, the principal quantum number describes the energy level. As we increase in energy levels, the electron is further and further away from the nucleus. So on the right-hand side here, something with a small principal quantum number has a very small energy level. On the right-hand side, a larger quantum number results in a larger volume where we were likely to find that electron. Okay, so the first quantum number is the principal quantum number that describes the energy level. We have another quantum number called the angular momentum quantum number that describes the shape of the orbital. So what you're going to find is that there are 4 different orbital shapes that are possible. There's what is called S, P, D, and F. S orbitals are spherical, P are dumbbell shaped, D are kind of shaped like kind of looks like a 4-leaf clover there, and then an F orbital looks like 2 4-leaf clovers that are kind of attached to one another. So these describe the shape of the orbitals where the electrons are likely to appear. The magnetic quantum number represents the orientation of the orbital. So for example, the s orbital, if you remember from the previous picture, is spherical. So you could only have one orientation of that. The p orbital can have three possible orientations, one along the x-axis, one along the y-axis, and another along the z-axis. Therefore, it has three possible orientations. The d orbital has 5 orientations, and the f orbital has 7 possible orientations. So you notice that they increase by 2 each time, 1, 3, 5, and 7, just like if you were counting odd numbers going up. Each orientation can contain up to 2 electrons. So the s orbital can hold 2 electrons, the p orbital can hold 6, d can hold 10, and f can hold 14. The last quantum number is the spin quantum number, and that indicates the spin state of the particular electron. This simply differentiates between electron pairs that exist in different orbitals. We talked about that there are 2 electrons that can exist within each orientation. Therefore, we need to be able to differentiate between those. So we say that one has plus 1/2 spin in one direction, and the other has a minus 1/2 spin in the other direction. So keep in mind that I'm not going to ask you to memorize any of the quantum numbers of any of the electrons, but you do need to keep in mind that electrons do exist in those 3-dimensional orbitals. There are different orientations of those orbitals, and those are the regions where electrons are most likely to be found. We're going to utilize this information in the next video to describe the locations of the electrons in different atoms on the periodic table. So long story short, electrons do have wave-like properties. They also have particle properties, which is why they have that wave-particle duality. They exist as both. The speed and position of an electron cannot be known simultaneously, as that is the Heisenberg uncertainty principle. Orbitals show probable locations of electrons, and the quantum numbers that are discussed indicate the properties of the individual orbitals discussed. So hopefully you have a little bit better understanding of this particular topic. I know it's a bit confusing. We're going to move forward with this and talk a little bit about electron configurations. That is, where are the electrons located in specific atoms next time you watch this video. Have a great day, guys. We will talk to you later. Bye-bye.